We start with a vector in space. It has some magnitude and it has some direction, but it's just in space. We can't tell how long it is compared to anything else, and we can't tell what direction it is compared to any coordinate system at all. It's just a vector in space. How do we do anything with that vector? We need to assign first a coordinate system. So here is our vector with a coordinate system. We've defined an x-axis, a y-axis, and a z-axis, straight up and down. And so our vector starts at the origin of this axis, which is convenient, and proceeds some amount of magnitude in some direction that we can now define as theta. The angle we've defined here is the angle from our z-axis to our vector. And we can see where it resides in this coordinate system. We need to go further. So here, we've identified the component vectors that make up this vector. So this red vector A is an amount AX in the X direction, an amount AY in the Y direction, and an amount AZ in the Z direction. And so now we have component vectors. We can break up this vector into each of its individual coordinates, but we still don't know how long this vector is really. We know its direction pretty precisely, but we don't know how long it is. We know its components for each coordinate that we've defined, but we have one more step to go. And that is to define unit vectors. So these gold vectors here are labeled with x hat, y hat, and z hat. And they tell us what one unit in each of those directions is equal to. That's what the hat is. And it's just a base reference to compare other things to. So by definition, and you can call it our definition, we are defining x hat to be one amount, one unit in this direction. So whatever the length here is, physically, we're calling that 1. Just like we call whatever the length of a meter stick 1 meter. And we're calling this length 1 in the y direction, and this 1 length in the z direction. And so now we can properly figure out the lengths of our component vectors. It's some multiples of these gold hat vectors, our unit vectors. And then we can find the total length of this vector in this coordinate system that we've defined if we find the magnitude of the total vector using our component vectors. And that's what we are going to do. So the magnitude of a vector A you find using A's components. So if we have a vector A, this sufficiently up out of the way, at A is equal to an amount AX times x hat plus AY y hat plus AZ z hat. And now you might be able to make some sense of what you may have seen before to calculate the magnitude. And to calculate the magnitude, we would write A, bars on either side, is equal to the square root of AX squared plus AY squared plus AZ squared. That's the magnitude. So if you have the components, it's fairly simple. So let's do an example real quick. Let's say that we have a vector A, and A is equal to 2x hat minus 4y hat plus 3z hat. To find the magnitude of A, you do the square root of 2 squared plus negative 4 squared plus 3 squared. And if you calculate that out, you should get the square root of 29. We can compute the angle the vector makes with an axis using trigonometric operations. So, the cosine of the angle theta that we defined earlier is equal to AZ over the magnitude of A. That's just a trigonometric triangle, right triangle, which is equal to 3 over square root of 29 that we calculated earlier. And this works out if you do the inverse cosine or the arc cosine. Theta turns out to be 56.15 degrees. Make sure your calculator is in degrees if you're working with degrees, and radians if you're working with radians. If we do use degrees, we'll often, or if we do use angles, we'll often be in degrees. We can also add vectors with their components. So if we had a vector A equal to, you can write it in this form as well, 2 minus 4, 3, right? And we had a vector B equal to 6, 7, negative 10. Then A plus B would be adding like components. A plus B would be adding 2 plus 6 x hat plus negative 4 plus 7 y hat plus 3 minus 10 z hat. And so that would be the vector 8, 3, negative 7.